Convergent sequence,
Convergent
Cauchy
sequence.
sequence.
Yes, convergent sequence in metric space. Okay, so next one. The next topic is the complete metric space. So before going to the complete metric space, so first of all we'll see the example. So here the example is, so we'll start with the usual metric. So usual metric means that is the real analysis. So here I'm taking the usual metric, that means the d of x comma y is equal to mod of x minus y for all x y belongs to real numbers. So this one we know that this one is the usual metric. So now is it complete metric or not? So complete metric means if so every Cauchy sequence if it is convergent, the type of metric we call as the complete metric space. Observe in the previously we have seen the Cauchy sequence. In the usual metric, every Cauchy sequence must be convergent. But in another metric, so maybe Cauchy sequence may be not convergent. For example, if it is I'm taking the rational numbers, so that is the Cauchy sequence, it is not convergent. So that is not a complete metric. So complete metric means every Cauchy sequence convergent in the same metric. We call that type of metric is we call as complete metric. So simply suppose it is our metric space. Suppose here there is a sequence Sn. If it is convergence to itself in this one, we call complete. Suppose here it is sequence, it is convergence to some another point. So it is not a complete because the convergent point is not in the metric space. If it is inside, we call that is the complete. Otherwise, that is not a complete metric space. Example, or that means a usual metric I am taking. So usual metric always it is the complete metric space. That means every Cauchy sequence must be convergent sequence in the usual metric. Next one, same. Instead of usual metric I am taking the, instead of r I am taking the ax. X is here I am taking the close interval 0 comma 1. So 0 comma 1. Now I am taking a sequence is 1 by n. So 1 by n is here the, we know that is the Cauchy sequence. Now check the limit of this sequence. So the limit of the sequence is 0. So 0 is belongs to x. So 0 is belongs to x. So this one is now a complete metric space. Similarly, I am taking one more sequence, that is the 1 minus 1 by n. So it is the Cauchy sequence. This is converges to 1. So 1 also belongs to x. So this x comma d is a complete metric space. But instead of, suppose here I am taking x is equal to close interval 0 1. If I am taking open interval 0 and 1 or semi open 0 1 or semi closed 0 1. Okay, now we will see the results. Yes, okay. Yes, so here see the results. So here the x is equal, I am taking the open 0 and closed 1. Now here I am taking x, the sequence is 1 by n. So 1 by n is the Cauchy sequence, we know that. But observe the limit of this one is 0. So 0 is not belongs to x. So what is the conclusion? So it is not a convergent sequence. It is the Cauchy sequence, but it is not a convergent sequence because 0 is not belongs to the x. So this one is not a complete metric space. Next one, same. If I am taking the closed 0 and open 1, same I am taking the one more sequence 1 minus 1 by n. So we know that this is the Cauchy sequence. Now what is the limit of this sequence? The limit of the sequence is 1. But 1 is not belongs to x because open 1. So closed 0 and open 1. So 1 is not belongs to x. So this x comma d is not a complete metric space. Okay. Okay, now so that is the under the usual metric. Now if I am taking the discrete metrics, because always we have to compare with the discrete metric. In the discrete metric already we have seen in the previous. So if b of a comma 1 by 2, it is always single term set a. If b of a comma 1, it is also single term set a. b of a comma 3 by 2, if it is more than 1, it is entirely metric space. So either single term set or whole metric space, it is the open ball in the discrete metric. Now come to the, I'm taking the discrete metric. So I'm assuming that x is the Cauchy sequence. X is the Cauchy sequence. Now I'm taking the epsilon is equal to 1 by 2. That means the distance is 1 by 2. So distance 1 by 2 means, so the after n not term onwards, each and every term must be the equal to equal. So this one is the, this Cauchy sequence is converges to some xn naught, xn naught. If I'm taking, suppose epsilon is equal to 1 by 2, okay, that is xn naught, single term set. Suppose if epsilon is equal to 1, epsilon is equal to 1, then it is also same, it is converges to xn naught. If epsilon is equal, suppose greater than 1, it is entirely our metric space. So already we know that logic. That means the conclusion is here discrete metric always it is the complete metric space, because here you can take any Cauchy sequence in the discrete metric, always that is the convergent sequence only. So convergent sequence, that is the observation. So here observe in the previously. So here x is equal to open 0 and closed 1, and x is equal to closed 0 and open 1. Under the usual metric, these two are the not a complete. But if I am taking suppose discrete metric, so observe under the usual metric this is not a complete, but in the discrete metric this is the complete. Next one, under usual metric here the q comma d, it is not a complete under usual metric, under usual metric so is not a complete metric space, complete metric space. But if it is discrete metric, so these all are the complete metric space. That means the conclusion is discrete metric space is always complete, no need to verify. Okay, so last class ఏమని డిస్కస్ చేసామండి, in the discrete metric each and every set is every subset of x must be open, and every subset of x is closed also. And one more point here, discrete metric is always complete metric space. That is the conclusion, complete metric space. Okay, just remember these 3 points. So these two example already over. Okay, yes. Now observe this one is in the usual metric it is not a complete, but in the discrete metric it is the complete, because in the usual metric, so in the usual metric our sequence is 1 plus 1 by n whole power n. It is tends to e, but e is not belongs to this q. So it is not a complete metric space in the usual metric, but it is complete metric space in the discrete metric. That is the conclusion. Okay, now we'll see the few examples same. So before that, now just see the examples. Here I am taking the x is equal to real numbers, and x comma d if I am taking the usual metric. So usual metric, so we know that is always a complete metric space. But in place of x is equal to r, if I am taking the closed interval 0 1, then so this one also complete metric space. But if I am taking, if it is not closed, that means it is the semi open or semi closed, then those two are the not a complete metric space. Okay, next one come to y is equal to -1 to +1, so this one also not a complete metric space. That means the what is the observation of these examples? Observe the second one is here the a complete metric space. Now we have to verify the relation between x and y. So here the y is the subset of x, and moreover, and this closed interval 0 1, it is the closed interval or closed set. Okay, that means the conclusion is, so if x comma d is the complete metric space, If Y is the subset of X and closed, if and only if that is always a complete metric space, complete sub. So that subspace must be the complete. Or if it is suppose the subspace Y of X is the complete, definite, that is the closed. So this one is the if and only if condition. Okay, so this point we have to observe. And previously now we have seen the properties. Just again here we'll discuss the properties same. So what is the definition of the complete? So complete means every Cauchy sequence is convergent, that we call it is the a complete metric space. That is okay, already we know that from the definition. But if suppose come to here, Cauchy sequence is convergent. So convergent means obviously that is the Cauchy sequence has convergent subsequence. If it is already convergent sequence, definitely subsequence also, definitely that is also convergent. Okay, so that means now we will add this all. If suppose x comma d is the complete metric space, every Cauchy sequence in X has convergent subsequence. Okay, that point we have to write here. If it is x comma d is the complete metric space, definitely every Cauchy sequence must be convergent if and only if every Cauchy sequence has convergent subsequence. Okay, so these all are the if and only if condition. Just to remember this point, sometimes they will ask the direct questions, okay, in the exams. Okay, now this one is about the metric, complete metric space. Next one, before going to the next one, just to see the example. Now example here, x is equal here the real numbers and I'm taking the usual metric. So we know that usual metric is always complete metric space, already we know that. Now what I'm taking here, I'm taking here the a closed interval minus 1 by n2 plus 1 by n. Now we will collect the all the closed intervals. The first one is the f1 is equal minus 1 to closed interval minus 1 to plus 1, and f2 is the minus closed interval minus 1 by 2 to plus 1 by 2. F3 is the minus 1 by 3 to plus 1 by 3. Now I am taking the intersection of all this infinite number of the closed sets. Then what will happen? So intersection of minus 1 plus 1 and minus 1 by 2 plus 1 by 2 minus 1 by 3 plus 1 by 2. So intersection of this all, it is gives a single term set. So single term set, so this is always non-empty. Now come to the statement. What is the observation here? So here we have Fn is it is sequence of intervals. What type of intervals? It is the closed intervals. Closed interval means here it is the closed sets. Closed sets. So now let Fn be a decreasing sequence of non-empty closed subsets of a complete metric space. So from the complete metric space, I am taking the sequence of the closed sets like this, and the length of the this interval is tends to 0 as n tends to infinity. That means after taking the n tends to infinity, so the length of the interval 0 tends to 0. Then definitely the intersection of all these intervals must be non-empty and it contains only one point, that is the it is a single term set. The intersection of these all closed sets must be the single term set. So this one is the contour intersection theorem. Okay, now this one is the a statement, so it is related to the complete metric space. Next one. So before going to the next one, now we will see the denseness. So dense set is again related to the real analysis. Now come to here. So anyway, so we will start with all the problems with the usual metric. Here x, so x is equal to real numbers and I'm taking the usual metric. So usual metric means d of x comma y is equal to mod of x minus y. And this is a usual metric,
Yes, sir.
always it is the Complete metric space already we know that. Now what I'm taking a subset of
Sir,
this.
excuse me, sir.
Madam
Someone
చెప్పండి.
is unmuted. Someone is unmuted. Tell him to.
Just a minute. Just a minute. Okay, ma'am. Thank you, ma'am. Yeah.
Okay, sir.
Okay. Now here, now I'm taking the A subset. So subset of X. So here I'm taking the subset is the rational number. So rational numbers is a subset of real numbers. Now I'm collecting the limit points. So limit points of this Q, not interior points. So limit points. Limit points of these rational numbers, we know the total real numbers. And the closure of Q. So closure of Q means it is the both union of rational number and derived set of Q. So derived set means set of all the limit points. So we call it is the closure of Q. So closure of Q. So when, so by taking the Venn diagram, okay, assume it is the X is the metric space. Now this is our some set yes, assume or D something. Okay, assume it is the some yes, assume. So this is S and the derived derived set of S. So it is, we call it is the all the limit points. All the limit points means it is includes this boundaries also. And closure of S means it involves both bound, it is includes the boundaries also. Now this one is the closure of, okay, so it is the extra points are derived set the point, that means limit points. So limit point of S and S is the closure of S. Similarly same interior. So interior means same. I'm taking uh, assume this is our metric space. X is the metric space and this is our set S, set S like this. It is a set S. Now I am taking the interior. So interior means it is avoids the boundary points. This one is the S not. Okay. So closer and adjust to it is covers the total boundary points. That means boundary points and ఇక్కడ meaning ఏంటంటే లిమిట్ పాయింట్స్ ని యాడ్ చేసుకుంటుంది. నెక్స్ట్ వన్ ఇంటీరియర్ పాయింట్స్. సో బౌండరీస్ ని జస్ట్ వదిలేస్తాయి. సో దట్ మీన్స్ ఇట్ ఈస్ నౌ బికమ్ ఏ ఓపెన్. So closure means it is always it is the closed because it is includes the limit points. Okay. But now come to the our topic. The what is the here the closure of Q. So closure of Q means it is the union of both rational number and derived set. Now it is the real numbers. Okay. So rational number. So closure of here Q is equal real numbers. So that means here the conclusion is suppose here S is suppose any set and the closure of this AC is equal entire metric space, we call that subset is dense set. So dense set means you can take AC is any subset of metric. The closure of this AC is equal to it is entire metric space. We call that is the dense set. For example, here the rational numbers. So rational numbers is a subset and the closure of this rational numbers entire metric space. So this Q is we call as the dense set. Similarly, not only rational numbers, irrational numbers also same satisfy same property. Observe here rational numbers. So the derived set of the rational numbers is entirely real numbers. Now the closure of this rational numbers is entire real numbers. So this one also we call it as a dense set because the closure of these irrational numbers entirely real numbers. So this irrational numbers also dense set in usual metric. Okay, in the usual metric. Next one, don't confuse. So next one. So before going to the next definition, now just see the example here. Now anyway, now we'll start with usual metric only. So I'm taking x is equal to real numbers, x is equal to real numbers, and x comma d is a usual metric. So d of x comma y is equal to mod of x minus y. I'm taking one sequence is s is equal to 1 by n. And what is the derived set of this s? So now the limit of this 1 by n is 0. That means the derived set of this s is single term set 0. Now the closure of this s is both s and derived set. That means the 1 by n such that n belongs to natural numbers union single term set. Now this one is the closure of s. So closure of s. Now what is the interior of this s? Interior. So interior means here observe here interior is completely empty set. Observe interior means you can take the open ball, so that you can take any open ball. That open ball is not in totally subset of this closure of a. So here there is no interior point of this closure of s. Similarly same, I'm taking s is equal a single term set. S is equal to single term set. So s is equal to single term set. Also the derived set of this s is empty, and the closure of this s is, and here the interior of this closure s is, observe here the empty. So the conclusion is, if the interior of the closure of s is suppose empty, we call that is the no weight dense set. That s we call as a no weight dense. The first one is, if s closure of s is equal to entirely real numbers, or s entirely metric space, we call as the dense set. If the closure of s, the interior of the closure of s is suppose empty, we call that is the no weight dense set. Okay, so that is you have to remember. Okay, now come to the second example. Here second example, s is equal to here the single term set. Now the derived set of the single term set is empty, and the closure of this s is the single term set. Now this one is the nowhere dense. That means the conclusion is from this one, if you can take any finite set in the usual metric, always that is nowhere dense. That is the conclusion. So same in the usual metric, rational numbers and irrational numbers are not a nowhere dense. These all are the dense sets. Okay, that is the observation. Okay, now so nowhere dense means, what is the definition of the nowhere dense? The interior of the closure of S is empty, that is the nowhere dense. Okay, now just to see the example, now here I am taking x is equal to rational numbers. X is equal to rational numbers. I am taking same in the usual metric. Usual metric. So usual in the usual metric. Now the rational numbers. In the rational numbers, I am taking the a rational number. Assume the a belongs to rational numbers. I am collecting the all the single term sets. Now it is the rational number, always it is the countable. We know that countable. Irrational numbers uncountable. So countable set. That means here I am taking the single term sets of all rational numbers. Those all are the countable sets. Countable. Now the again the previous one. If it is finite set, that is always nowhere dense. Nowhere dense. That means that here the rational numbers we can write the union of single term sets. The union here the countable, because the rational numbers are countable. That means here the rational numbers we can write the union of single term sets. That means the union of nowhere dense. If we can write suppose any metric space is the union of countable union of nowhere dense. That type of metric is of first category. Okay. So first category. What is the definition of the first category? So here x comma d is any metric space is said to be ఒక్క నిమిషం అండి. Okay. So here observe x comma d is said to be any metric space is said to be the of first category if it can be written as countable union of nowhere dense. If the metric space we can write the union of, or union of means a countable union of the nowhere dense. That metric space is said to be of first category. So first category is simple, just it is the, we can write that metric space is the countable union of the nowhere dense sets. What is the nowhere dense? Nowhere dense is nothing but the interior of the closure of S is empty. It is the nowhere dense. Dense means closure of S is equal entire metric space, that is the dense set. Okay, that is the first category. Next one come to the same like the second category. So that is very simple. If it is not first category, that is we call as a second category. That means if it is not countable union of nowhere dense, it is not countable union of the nowhere dense, because that is the second category. Okay, second category. Second category means, so here the a metric space x comma d is not a first category, so is called as, is said to be of second category. So example. So here x is equal, I am taking the rational numbers, I am taking the usual metric. Usual metric already we have seen. This x is equal, we can write the, that means the rational numbers we can write the union of single term set, and the single term set finite set is always nowhere dense. That means we can write countable union of nowhere dense. But in place of suppose the rational numbers, if I am taking the real numbers same. So R is equal, I am taking the single term sets. So single term sets, and R is uncountable set. R is uncountable set. R is uncountable set. That means here the, I'm taking single term sets. Single term set. So how many sets we have? Uncountable number of sets, not countable. So it is not first category. Not first category means it is the second category. That means the conclusion is either first category or second category. Either adi untundi idi. Okay. Next one. So don't confuse here. First category means if we can express the union of countable union of the nowhere dense, that is the first category. Otherwise it is the second category. Now, so first of all see the examples. Example here, the x is equal real numbers, and I am taking the usual metric. So we know that according to the previous one, this one is the complete metric space. Complete metric space, okay. And observe, and here R is equal, it is the union of single term set we can write, but the union of the single term set is the uncountable. So this is a second category. So it is a second category. Next one same, x is equal, I am taking the close interval 0 1 and under usual metric. So this one also we know that it is the complete metric space because it is the closed set under the usual metric. Okay, now here x is equal to open, sorry, close interval 0 1. Now I am taking the single term sets. So close interval 0 and 1, you can take the all the points. That means the how many points we have? Uncountable number of points, because this one is the uncountable set. So uncountable set. So here also it is the, we have the union of uncountable number of single term sets. So this one also second category. What is the conclusion of this one? So the conclusion is, If suppose x comma d is any complete metric space, definitely that x comma d must be satisfies the second category. So it is second category. That means it is not first category. Okay, that is the conclusion. So every complete metric space is of second category. So that is the base category theorem. So base category theorem statement is every complete metric space is of the second category. That is the conclusion. Yes. Okay, and already we have seen in the previous. So complete metric space is second category. Okay, that's the previous one. So this is our statement. So if x comma d is the complete metric space, so definitely that is the second category. Now come to the statements. So if suppose P implies Q, what is the contrapositive? Contrapositive is the
Negation Q
negation
implies
P implies the
negation.
negation Q. So what is our statement? If x comma d is the complete metric space, definitely x comma d is of a second category. Now contrapositive. So if x comma d is the not second category, definitely that is not complete metric space. Or not second category means it is definitely first category. That means if it is a first category, then definitely x comma d not complete metric space. Now we'll see the example. So x is equal to, I'm taking the rational numbers. We know that this one is not a complete metric space. But now we'll see the according to the this statement. What is statement? Now x comma d of x comma y is equal to, I'm taking the mod of x minus y. X comma d is the first category. We know that this one is the first category because these rational numbers we can write the union of single term sets. The countable union of the no-weight densities. So this one is the first category. First category means now this metric space is not a complete. Okay, just మీరు ఒక అది ఫస్ట్ కేటగిరీ సెకండ్ కేటగిరీ ఐడెంటిఫై చేస్తే then we can easily identify whether that is the complete or not complete. So here the if it is suppose x comma d is a first category, so by statement we can say that x comma d is not a complete metric space. Okay, so now this one is the related to the complete metric space. So next one, next one more topic. Yes, open cover. So next one related to the compact. So before going to the compact, now what is the definition of the cover? Cover and definition ఏంటంటే cover. Cover. We'll use the cover. What is the meaning of cover? Suppose now we have a set. So okay, now this one is the a set x comma d. Okay, yes. So this is the set, assume A. A is the set. A is the set. Now what I'm taking, so assume it is the U1 and assume it is the U2 and assume it is the U3 and assume it is the U4, assume it is the U5, assume it is the U6 and assume it is the U7. That means the conclusion is here this A is covered by U1, U2, so on up to U7. Or so this A is the subset of union of I is equal to 1 to 7 UI. Okay, so simple గా just ఈ సెట్ A ని U1 నుంచి U7 వరకు కవర్ చేస్తుంది. Okay, so this is the light observation of the cover. So now come to the mathematical. So mathematical here, suppose a subset AB is the subset of the metric space, A any subset, and a collection of G lambda. So is the lambda is a index. Index is maybe infinity or maybe finite, we don't know. That depends on the metric space. Here the G lambda is the subset of X. That means it is the collection of subsets. That means the U1, U2, so on up to UN are the subsets of X. Is said to be the covered by A if A is a subset of this U, so union of this GI. That means here this U1 to up to U7 is the uh, this collection is cover of A only, and this cover is sometimes maybe finite or sometimes infinite. Okay, and we can write like this also. If the family of this G lambda covers entire X, that means sometimes it covers the only some A, B, C, some subsets. But if it is covers entire metric space, sometimes maybe it is covers the entire metric space. That is equal to X is equal to union of all these sets. Okay, that uh, that cover we call as the open cover. Yes. So we call that is the open cover. So open cover means just a small change. The previous one that is the cover. If here subsets are suppose open sets. So here we are assuming the only subsets. That subset may be closed or may be open or maybe other sets. If it is suppose open sets, we call that cover is open cover. That means here the A is any subset of the metric space. The collection of the open subset of X is said to be the open cover, and if A is the subset of the union of this all the open sets, we call it is the open cover. So cover చేస్తుంది కానీ ఎలాంటి సెట్స్ కవర్ చేస్తుంది, ఓపెన్ సెట్స్ కవర్ చేస్తుంది. సో we call it is the open cover. Next one, open cover. Okay, next one, finite cover. Finite cover means, so for example the first one. Now in the first example what I am taking, u1 u2 so on up to en. Now this only a covered by this u1 to up to un. So this cover we call as the finite subcover. Okay, so here they come to the definition. A's collection G lambda of the subset of x comma d covers A, where A is a subset. Then sub collection. So okay, already this A is covered by this family of the sets, but in the family of the sets I'm taking the only finite number of the sets. That means the G lambda 1, G lambda 2, G lambda n is said to be the finite subcover if A is the subset of this U, so union of I is equal to 1 to n G lambda. We call it is the finite cover. But sometimes finite subcover, so finite open subcover. Finite open subcover. So first of all, what is the cover? So cover means just it is A is the subset of the family of the union of the family. And the next one, open cover. If the family is the set of all open sets. Next one, finite subcover. So not only all the subset will take the only finite number of sets cover the whole set, we call it as the finite subcover. Sometimes open finite subcover. Open finite subcover. If suppose every open cover of A as finite subcover. So anyway, you can take suppose set A as the A open cover as open cover. If it is as the suppose finite subcover, that type of set we call as the compact set. For example, here I am taking X is called close interval 0 1 and I am taking the usual metric under the usual metric. Now we'll check, is it a complete compact set or not. Now we'll verify. So is the close interval 0 1. So close interval 0 1, I'm taking uh, finite subcover. So minus 1 by 2 to plus 1 by 2 union 0 to 3 by 2 union 1 by 2 to 1 and union 3 by 2 to 4 by 5. Okay, observe 1 2 3 4 5. So now it is the open cover. So this open cover, so 1 2 3 4, but in this 4 no need to take the 4, so just take the minus 1 by 2 to plus 1 by 2 and 0 to 3 by 2. It covers A. That means this cover has the finite subcover. So finite sub, how many elements, how many intervals we have? Only 2. So this open cover has the finite subcover. So for like this, you can take any open cover of A has the finite subcover. That A is called as the compact set. So this closed interval 0 comma 1 is the compact set. So by using the definition, that is not easy to identify the set is the compact. For that now we will see the properties. Okay, but before going the properties, now we'll see the property in the usual metric. Usual metric. Observe in the previous example. What is the previous example? Closed interval 0 1. It is the compact. Next one same, closed interval 1 comma 5. This is also compact. But observe the structure of this set. The structure of this set is, it is the closed set and it is the bounded set. Closed set and bounded set. That means the conclusion is, in the usual metric you can take any set which is closed and bounded. Closed and bounded. Definitely that set must be the compact set. Okay, okay, these two. Okay, now come to the third example. A is equal to 1 by n such that n belongs to n union single term set. Is it closed set or not? Closed sets, because the derived set of this A is the single term set and the closure of A is equal to A. So closure of A is equal to A, we call it as the closed sets. Interior of A is equal to A, we call it as the open set. Now this is the closed set. Closed set. Is it a bounded? Bounded, because the lower bound is a 0 and upper bound is 1. Now it is a bounded set. That means this is now closed set and the bounded set. So closed, bounded, and usual metric, it is definitely compact set. Okay, so compact set is always closed and bounded in the usual metric. You can take any compact set in the usual metric. So definitely that is the closed and bounded. Now see this one. I'm taking one more. Okay, so if A is equal to suppose minus and plus infinity. So it is the closed but unbounded. So this is not a compact. That means the real numbers is not a compact. How? Just see the example. So see the example. Suppose here I'm taking the open cover. So open cover is minus 1 plus 1 union minus 2 plus 2 minus 3 plus 3 so on. So it is the A open cover. So open cover is union of n is equal to 1 to infinity minus n to plus n. Now it is the open cover. But this open cover not admits the finite subcover. So we don't have the finite subcover. So here we have the finite subcover and here also finite subcover. But here we don't have the finite subcover. Okay, that means if it is one of the open cover is not finite subcover, we call that is a not a compact. Okay, that is the conclusion. So the conclusion is, so if it is the closed and bounded, that is the compact. If it is unbounded, not compact. It is not closed also, not compact. So like that you can easily identify. Okay, now this one is related to the compact. Okay, now few more properties and examples on the compact. Okay, next one is the compact means every open cover has the finite subcover. We call it as the compact set. Now come to the compact metric space. So the previously just we have seen only a subset. Now if the metric space satisfies the same property. That means every open cover of metric space X has the finite subcover. We call that is the compact metric space. Compact metric space. For example, now X is equal, I am taking the closed interval 0, 1, and X comma D, we know that usual. Now I am taking the usual metric. Usual metric means here the D of X minus Y, and we know that this X is equal closed interval 0, 1 is the compact set. Why? Because it is the closed and bounded. Closed and bounded. And this one is the metric space also. So this one is the compact metric space. Compact metric space. This is the one of the example of the compact metric space. Now we'll check here. In the previously we am taking the X is equal to close interval 0, 1. Now that is the compact. Now in place of X I am taking the real number. Is it a compact metric space under usual metric? Now we'll check. So here I am taking the first of all two examples. The first example here I am taking the open cover. Open cover union of n is equal 1 to infinity minus n to plus n. This is the open cover. Here we don't have the finite subcover. I'm taking the one more cover. One more cover means minus infinity to minus 4, minus 5 to 0, and minus 6 to 1, and minus 2 to 0, and 0 to 7, and minus 1 to infinity. So in this one, 1, 2, 3. So these three sets enough for cover these real numbers. So this open cover has a finite subcover. But observe here, not every open cover has the finite subcover. So here, okay, this open cover has a finite subcover, but here this open cover not has a finite subcover, so it is not a compact. That means every open cover is finite subcover is compact, but one of the open cover is not finite subcover. We call that is the not a compact set. But this one relates the metric space. So this R comma tu is not a complete metric space. That means usual metric space is not a compact metric space, but usual metric is, that means R comma du is complete metric space. That is you have to remember. That is you have to observe. Okay, usual metric is not compact, but usual metric is complete metric space. That is observation. Okay. Now the previously we have seen if it is set is the closed and bounded, definitely is the compact. Okay. Now come to the example. So just see the these two examples. X is equal to, I am taking the closed interval 0, 1, and X comma D is the usual metric. Always that is the compact metric space. Similarly same. Y is equal to closed interval 1 by 2, 3 by 4, and I am taking the usual metric. So definitely that is also compact metric space. So from these two examples, what is the conclusion? The conclusion is if Y is any closed set and Y is the subset of compact set, always that is the Y also compact set. That is the conclusion. Okay. So statement is a closed subset of the compact metric space always a compact set only. Now here I am asking a question. Suppose here I am taking the metric space is the compact metric space. Okay. I am taking the two subsets. One is the closed set and another one is the compact. Now, is it the intersection of this closed and compact is compact or closed or neither closed or nor compact or both? One is the closed, another one is the compact intersection of these two. Now we'll see. examples. So relate to the discrete metric. All observe in the previous all the problems are we have seen under the usual metric only. Now we'll see the problems on the discrete metric. Now come to the first one. X is equal to close interval 0 1 under the discrete metric. We know that. So if the open ball with radius is 1 by 2, it is single term set. Open ball with radius is 1, single term set. Open ball with radius is 3 by 2, it is the entire axis. Now here I am taking the relate to the compact. So metric space is compact metric space or not. Now we will verify. Suppose here I am taking a open cover. Open cover is balls. Here the open sets means here the balls. Balls is the open set. Now open ball is x comma 1 by 2. It is the single term set. Single term set, but is the close interval 0 1. Now how many single term set we have? Uncountable. So and it is the open cover. Open cover, but observe this open cover does not have the finite subcover because here I am taking the each and every point. Okay, if the one of the point is not there, it is not equal to x. So this open cover does not have the finite subcover. Okay, if it is suppose distance is 1 by 2. If the distance suppose I am taking the 3 by 2, assume 3 by 2, then what will happen? It is equal entire x. So in that case, so this open cover has the finite subcover because only one ball is enough. That means the conclusion is not every open cover has the finite subcover. If the radius is more than 3 by 2, every open cover has the finite subcover. If the radius is 1 or less than 1, the open cover not has the finite subcover. That means the conclusion is this is not a compact set. So compact set. That means the not a compact metric space. So x is equal to close interval 0 1 is not a compact metric space. Here metric is the discrete metric. That means the conclusion is here. So before going to the conclusion, now just see the example. The previously observe the set is close interval 0, that is infinite set. Now here I am taking, suppose here I am taking, suppose set A is the compact set. Sometimes maybe in the discrete matrix, suppose we'll take the compact set. Now what is the status of that set A? Now we'll check here. So here the open cover, I'm taking the open cover B is equal to x comma 1 by 2 such that x belongs to A. Now I'm taking the radius is 1 by 2. So 1 by 2 it is a single term set. It is the open cover. So already it is clearly given A is the compact. So A is the compact means every open cover has the finite subcover. Every open cover has the finite subcover. So definitely this A must be the finite. Otherwise it will not satisfy. That means the conclusion is if suppose A is the compact set in the discrete metric, definitely that A must be the finite. Otherwise it is not a compact. That is the conclusion. Okay, in the previously in the discrete metric every subset is the open set, every subset is the closed set, and metric space always it is the complete metric space. One more point is if A is the compact set in the discrete metric, always that is the finite set. Okay, that is the observation. So observe this point is x comma d is the discrete metric space and A is the subset which is the compact. Definite that is the finite set only. Okay. Now what is the converse? So converse is work or not. Now we'll take. Suppose here A is any finite set. A is any finite set. Definitely that is always a compact set. That is under any metric. Okay. So if A is finite set, definitely that A must be the compact set under any metric. Just remember this point also. Yes. Okay. But when it is the satisfies, the previously third point is A compact, definitely finite. Finite means definitely compact. That means in the discrete metric, if it is A is the compact set, if and only if A must be the finite. If A is an infinite set, if and only if it is not a compact. Not a compact, definitely it is the not infinite set. So infinite set. Now we'll see the examples under usual discrete metric. Now the three examples. The first one is A is equal to 1 to up to 10. I am taking under discrete metric. A is equal to I am taking close interval 0 1 under the discrete metric. A is equal to I am taking the natural numbers under the discrete metric. Now this in these three, which one is the compact, which one is the not compact? Now the come to the first one. Here A is finite set. So this A must be the compact. Second one, this A is infinite set. So this is one is the not a compact. Here this A is infinite set. So this one also not a compact. Just to check whether that is a finite or infinite. If it is finite, compact. If it is infinite, not compact. That is the conclusion. Okay, one more point.
Sir,
Already, sir, madam, చెప్పండి మేడం.
sir, here 0, 1 is not compact means how you ఇది ఎలా చెప్తున్నాం సార్ ఇన్ఫైనైట్ అని?
మేడం క్లోజ్ ఇంటర్వల్ 0 to 1 మధ్యలో ఎన్ని పాయింట్స్ ఉన్నాయి మేడం? ఒకసారి కౌంట్ చేస్తారా మీరు ఎన్ని ఉన్నాయో?
ఓకే సార్.
So now the close interval 0 1 is the uncountable set. It is not a finite set, it is the uncountable set. And the
Yes.
natural numbers are, it is the countable set but infinite. So infinite lo mali two categories. One is the countable, another one uncountable. Okay? Real
Yes, sir.
numbers. మళ్ళీ రా ఒక్క నిమిషం అండి.
సార్ ఓకే సార్.
ఓకేనా మేడం?
గాట్ ఇట్ సార్.
క్లారిటీ వచ్చిందా?
ఓకే.
ఓకే.
ఎస్ సార్.
జస్ట్ మీరు అక్కడ ఆ సెట్ ఫైనైటా ఇన్ఫైనైట్ వెరిఫై సరిపోతుంది ఇన్ discrete metric.
ఓకే సార్.
Okay, the first one is the finite set, so compact. Second one is the infinite set, so not compact. Third one is infinite set, not compact. Okay, so no need to verify the definition, just use this property. Okay, next one. So before going to the statement, now see the examples. So here the x is real numbers and I'm taking the under the usual metric, and y is equal, here I'm taking the close interval 0 1. Observe this one is always compact, so close interval is always compact in usual metric because that is the both bounded and closed. Okay, this statement already we know that, but anyway again I'm writing. Suppose if y is the closed and bounded in the usual metric, definitely that is the compact. Compact set is always both closed and bounded in the usual metric. Okay, so not only usual metric, you can take the Euclidean metric space. In the Euclidean metric space also, if you can take r power n, so r n tuples Euclidean metric space, if A is the compact, if and only if that is the closed and bounded. కాకపోతే డిస్క్రిట్ మెట్రిక్లో అది వర్కౌట్ అవుతుంది మేడం, దట్ ఈస్ ద డిఫరెంట్. ఎందుకంటే ఇక్కడ ప్రీవియస్ ఎగ్జాంపుల్ చూడండి, దిస్ వన్ ఈజ్ ద A is equal to, observe in the discrete metric every set must be the open, every subset of x is both open and closed. That means these three are the open as well as closed, but observe these are not compact sets and all are the bounded sets. So except this natural numbers, this is the bounded set and this is the bounded set, that is the closed and bounded, but yet it is not a compact in the discrete metric, but in the usual metric it will work. Okay, don't confuse. Okay, Okay, now already we have seen the property. What is the property? Compact set if and only if there is a closed and bounded. But if A is the compact, so before going to the statement, now just see the examples. Yes, see the example here. The first example is here x is equal to, I'm taking the real numbers and a usual metric. So this one is the closed interval 0 1, it is the compact, so closed. Okay, no problem. Next one, x is equal to, here I'm taking the real numbers and I'm taking the discrete metric, and x is equal, y is equal to, I'm taking 1 2 3, so it is a finite set, and this is also compact. But observe here, these two are the closed sets. First one is a closed interval 0 1, okay, closed set. Second one is y is equal to 1 2 3, it is also closed, because every subset of the discrete metric space must be the closed, so this one also closed. Okay, that means the conclusion is, if A is any compact set, that is always closed set. Next one, converse. Converse is, now we'll verify. Now y is equal to x comma d usual metric, and x is equal to real numbers and x comma d is the usual metric, and y is equal to, I'm taking the closed interval. So closed interval 0 1, it is the compact. Now I'm taking one more example. Y is equal to x is equal to real numbers and x comma d is the discrete metric, but I'm taking y is equal to natural numbers. This one is the closed set, but not a compact. That means the conclusion is, if it is compact, definitely closed. But if it is closed, it need not be the compact set. Okay, in the general metric, but especially in the usual metric, if it is compact, definitely if and only if that is the closed and bounded. But in the general metric, compact must be closed. If it is closed, it need not be compact. That is the conclusion. Similarly, same, it is related to the closed. Next one, bounded version also. If it is bounded set, if it is compact set, always it is the bounded. But the bounded is need not be the compact. See the examples. Come to the first example. Now here I am taking x is equal to real numbers and I am taking the usual metric. Y is equal to close interval 0 1, it is the compact set. Observe, it is the bounded. Okay, I am taking the same example, same as the previous example. And x is equal to, here the real numbers, x comma d is the discrete metric, and y is equal to 1 2 3, it is the compact set. Observe, this is the bounded set. That means, observe here, if it is compact set, always the bounded set in any metric. Okay, that means the conclusion is here, observe here, the compact is always bounded. But what is the converse? Converse of the statement. Converse is, if it is bounded, is it compact or not? Now we'll verify. So x is equal to, I'm taking the real numbers under usual metric. X is equal to, I'm taking close interval 0 1, it is the bounded, compact, okay. Second one is z is equal to open interval 0 1, bounded, but it is not a compact, because in the usual metric only closed intervals must be the compact. Second one, come to in the discrete version. In the discrete version, x is equal to real numbers and discrete. Now y is equal to 1 2 3, so it is the bounded, and finite set. Finite set, every finite set must be the uh, compact in the discrete metric, so it is the compact. But z is equal to, here I am taking the close interval 0 1, it is bounded but not a compact, because it is the infinite set. In the discrete metric, only finite set is the compact. Infinite set must be the not a compact. That means the conclusion is, if it is bounded, it may be compact or may not be. But the compact always is the bounded. But so the conclusion is, from these two statements, what is the conclusion? If x comma d is any metric space, y is compact implies Y must be closed and bounded, but converse is need not be true. Need not be true. But in the usual metric, so converse is true. The Euclidean metric also converse is true. But in the general metric, so converse is need not be true. But compact is always both bounded and closed. But bounded and closed is need not be compact. Okay. So now anyway, now we'll stop. We'll see the remaining topic in the next class. In the next class, we will see the few examples on the compact, okay, under the usual metric and under discrete metric. Okay. Now anyway, we'll stop. So thank you to all. So the remaining topic we'll discuss in the next class. Thank you to all.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, ma'am.